Hello, everyone. My name is Caetano Miranda, the Director of the Education and Diffusion of Knowledge of the Research Center for Greenhouse Gas Innovation, one of the leading engineering research centers of FAPESP. Today, we are going to receive in our RCGI Colloquium series, Dr. Peter Johnston, a worldwide expert on the catalyst technologies. And to introduce our guest, I would like to invite Professor Liane Rossi, the Director of the Carbon Capture and Utilization Program at RCGI. Liane, please.
Hello, everyone. That's a pleasure to host today the talk from Professor Peter Johnston. I'll say some words about his biography. He received his PhD in 1988 from the University of Witwatersrand in Johannesburg, South Africa. And after that, postdoctoral appointments at Liverpool Center of Innovative Catalysis in Liverpool, and at Hull University in the UK. He holds an academic appointment at Hull University, and then he moved to an industrial career in 1996 with the heterogeneous catalysis group at Johnston Matthew in the UK. He currently holds a post as scientific consultant with Johnston Matthew Chemical Catalysis Business Unit in the UK. So his main scientific and technological responsibilities at Johnston Matthew include the development and scale up of supported platinum group metal catalysts, as well as base metal catalysts for a wide variety of applications with bulk and fine chemicals industry. It's very interesting to know that about 30 of the catalysts that he developed have been fully commercialized and have been manufactured and supplied in large scale in kilograms and multi-ton scale quantities. So as part of this, he has overseen the design and the construction of 3 dedicated catalyst production plants for the manufacture of some of these catalysts. Besides that, he is co-author of 8 patents, more than 70 publications, was supervisor of 14 PhD students, received many awards, and this is our great pleasure to listen to you today, Peter. And thank you very much for accepting our invitation. So the floor is yours.
Yeah, no, thank you very much, and it's a pleasure to give this talk to you, and thank you for the invitation to give the talk, and also apologies that we had technical problems last time, but hopefully we'll manage with the connection today. In this talk, which I try to get up, I really thought I'd give an overview of some of the work that we've done in the development and commercialization of gold catalysts for VCM production. And really, I thought this would give a nice balance and flavor of some of the work that we've done in translating some fundamental catalysis and seeing it through into commercial development and now into full-scale production. And so really to take you through this journey, which really has is sort of a summary overview of about a 15-year journey through from where we started to the present day. And as I said, by introduction, vinyl chloride monomer, or VCM, is a major commercial commodity as a monomer for the production of PVC, or PVC, which gets converted into PVC plastic. And PVC, as you'll know, is the 3rd highest selling polymer worldwide. It has a unique feature that it's a non-biodegradable plastic, so it's intentionally manufactured to have a long lifetime, and then, of course, maybe formulated into all sorts of forms and products. It's probably best known, certainly in Europe, for its use in things like plastic window frames, exterior cladding for houses, where again this long lifetime and rigidity and weatherproofing is of importance, but also in a whole lot of pipe and tubing applications, and then also as a insulator around electrical cables, etc. Of course, that's just selected of the many uses that it's used in. And if you look on the pie chart, you can see this is really the sort of rough breakdown of the use of plastic polymers around the world. So you find the biggest one is polyethylene, followed by polypropylene, then PVC, as I said, polyvinyl chloride, and then much smaller is polystyrene, and the rest of the plastics form about 16%. So it's a huge demand and use of polymer, and it's typically about 60 million tons are made per annum worldwide, and this growth in the industry is growing at about 5% per annum. So if we look at the processes to make for the production of VCM, there are really two main routes. And the first one, which is again the top title on the topic of this presentation, and this is actually the much older process in which you're doing direct hydrochlorination of acetylene in a single step reaction. And this is really starts from coal, where in the first step the coal is converted by usually the carbide process to acetylene, and now you have the direct addition of the HCl to the triple bond to form the VCM. And this process is largely run nowadays exclusively in China, and say towards 99% of the process run around the world. And of the Chinese capacity, it's about 80 to 85%. And this really dominates because of the large coal base in China. In the rest of the world, in particular in the West, about 99% of the VCM production is via what's known as the balance process. And in this, it's really a multi-step process in which now you're starting from essentially an oil feedstock, which you're converting in the first step to ethylene. And now you're doing a multi-step chlorination, oxychlorination to form ethylene dichloride. And then this is then cracked back thermally to VCM. And this is, again, out of this, the HCl that's cracked off is recycled back. So it's a very much more complicated process, but very efficient. And this is really used as an iron and copper catalyst. But really the interest for us, as I say, was in the hydrochlorination of acetylene. This process run in China from where coal is used as a feedstock. And you can see here the reaction. You're taking this acetylene, you're adding HCl across the triple bond. And this is really dominated as in China, and is really accounts for about 20 million tons of VCM and then PVC produced per annum. And this is really largely produced in over 90 plants in China, and a typical plant will have about 100 individual reactors, and of those, each reactor will have about 6 to 7 tons of catalyst, which is normally and currently is a mercuric chloride on carbon catalyst. And so this gives you an total installed capacity in China of about 21,000 tons of catalyst. So if you look this in the pictures here, this is just a schematic of a typical plant where you can see the lines of reactors. So you have a primary and second reactor, And on the other side of the central feed, you have another row of reactors, and the acetylene and HCl are brought in down the center manifold and say distributed to the different reactors, and then after the second reactor go back down into a polymerization plant. And a closer view you can see, and this is a slightly different plant, where you would have the reactor sitting as a fixed bed reactor, and you have again a primary reactor and a second reactor with the feed of the HCl and acetylene, and the VCM exits down the center line of the plant. Typically, the catalyst that's nowadays used is about a 4% mercuric chloride on carbon, and it's all based on a 3 millimeter diameter extradate. And the reactor is run as a typical shell and tube reactor, so you'll have several thousand tubes of catalyst sitting in the reactor. The typical performance and lifetime of the catalyst is about 6 months, and that gives you a total productivity about 1,000 kilos of VCM per kilo of catalyst. And in a typical application, depending on what the throughput and space velocity is used, so the catalyst will last anything from 6 to 9 months. But more significantly, the problem here is it's the largest use and actually also the largest loss of mercury worldwide in the process. And typically, there's several hundred tons of mercury are lost to the environment per annum. And this is really what became interesting for us, because this containment and use of mercury for this process has always and long been recognized as a major problem. And although there have been a number of improvements in the design for the reactor and process, this is still really a fundamental problem, especially with this amount of use of mercuric chloride and the sublimation and loss from the reactor and process. One of the new later technologies that has been done and improvements in this process is to thrift the mercury loadings on the catalyst down from the original 10%, and now they're running with a typical loading of about 4% mercuric chloride on carbon, but it's still in a huge use and loss of mercury. And this has become recognized as an increasingly big problem, not only because of the environmental aspects of this loss of mercury, but more significantly, in a lot of the Chinese and other mercury mines are becoming depleted and have been set for closure in the next few years. And of course, this is being driven from the United Nations Minamata Convention, which seeks to ban the use of mercury for VCM production. The challenge here is, and the goal set by the United Nations here was to ban the use of mercury in the use of this process within 5 years after a mercury-free alternative catalyst has been proven and shown to be technically and economically feasible. And this really we saw this and saw that this would be a real challenge and an opportunity for us to really look at, can we develop something that would be a viable alternative to this. So at the outset of our work on this, which was around about 2007, we knew that a 1% gold on carbon catalyst had been shown in the academic literature as viable and possible alternatives to the use of the mercuric chloride. However, when we looked at these, there were a number of features which presented themselves as challenging. And that was firstly that these catalysts were not hugely active, and certainly not sufficiently active to be commercially viable from a technical point of view, but also from an economic aspect. However, there was one very important good feature, was that the gold catalysts, just as the mercuric chloride catalysts, showed almost 100% selectivity. So the challenge for us was, could we develop a catalyst that would have a higher productivity and also have the commercial viability? So when we looked at these catalysts, we realized that actually also, from a catalyst manufacturing point of view, which was important to us as a catalyst supplier, that the only way, or the only activity that was achieved with these catalysts was a preparation by impregnation of a gold salt from aqua regia, which of course, as you'll know, is concentrated nitric acid and hydrochloric acid. So this was again immediately a challenge for us, where we recognized we would need to either minimize or completely eliminate the use of the aqua regia in the catalyst preparation, because for us to prepare a ton of catalyst using this published method would need about 500 kilos of aqua regia. So we would actually, if we used this method to prepare commercial quantities of catalyst, we'd be swapping one environmental problem with simply another. And also from an economic aspect, we recognized that, and especially as a change in the gold price from this very early work, where these catalysts required a 1% gold loading to have sufficient activity. So for us, we knew that we'd have to have a much lower gold loading for economic viability. So really the challenges for us were simply we needed a much higher activity, productivity, and of course either a much lower gold loading or a higher, much better performance. And the other part which constrained we had to again bear in mind that given that there is this existing infrastructure for this, that really the catalyst would have to be a drop-in replacement into these existing reactors, and would have to be capable to be run under the similar conditions to that of the mercuric chloride catalyst. Having or coming up with a catalyst that would be completely different and would require very different operation conditions would really be a very big limiting factor in the adoption of anything we developed. So really, this was the goals at the outset that we set off with. And if we look at the catalysts and the performance of the catalysts we had that were existing at that time, now this is now in lab scale testing. So we've taken a lab microreactor running at typical conditions, and again this typical low temperature condition that the VCM plants run at. You could see at a 1% gold loading, you get about 50% conversion when the catalyst is prepared from aqua regia. If we take the gold chloride, which was the common salt used for this, if you either prepare the catalyst from water, it has very poor activity, and just changing the aqua regia to either HCl or nitric acid, again, you got worse activity with, again, variations in the induction period. And again, an analysis of these materials showed us that from HCl, you got a better dispersion, but you got lower proportion of gold-3, which is the active component. Whereas nitric acid, you got a lower dispersion, but a higher proportion of gold-3, and that really explain some of the induction effects that we are seeing. Further analysis of the catalyst showed that the gold is deposited in a narrow eggshell or shell on the surface of the carbon extrudate, and you can see this is in these pictures. This is a cross section and then elemental mapping of the carbon extrudate. So, you know, remember, think of that as the cross section through the cylinder, and the gold is on the surface in the outer layer. A lot of surface analysis showed us that the catalyst was essentially gold, a mixture of gold 3 and gold 1. And again, from the performance point of view, you could see that the gold chloride cation is readily reduced to gold 0. And again, at this point, that was well established as the main mechanism for the deactivation of these catalysts. And that once the gold has been reduced to gold 0, it's deactivated and isn't recovered in use. And a lot of work up to this point for us, we had recognized that the limitation in the performance of the catalyst that we could get was really the limitation by the lack of stability of the gold chloride, the AuCl4, and in gold 3 as the active site. When you look at it again, we had done some in situ XAFs of this, and you could see, well, in the microscopy, you can see in the use of the catalyst, you can see the formation of gold metal centers, so the bright dots in the micrograph. And in the XAFs, you could see the reduction in the gold chloride component and formation of metal, you know, gold distances as formation of gold metal. And this really just progresses further during use. And so it again was consistent with all the early work that the deactivation and lack of stability with time on line is simply degradation of the gold chloride. So this really led us to consider what we might do to improve the performance of these catalysts and stability. And what we recognized at that point was we of course needed to maintain the high dispersion to get the high activity, but also we needed to increase the stability of the gold cation in the higher oxidation state. And what we then at that time postulated was that we needed to use a soft donor ligand, because that would again stabilize the gold in the higher oxidation state. And the two obvious contenders of this are the use of cyanides and then also sulfur-containing ligands. We avoided, and we didn't want to really explore the use of cyanides because of the toxicity of them, and you know, we felt that the industry would be very unwilling to adopt the use of a gold cyanide. So we felt, and we had known from other studies, that the use of sulfur ligands in these types of reactions could be beneficial and actually don't necessarily poison the catalyst. So we really started then to prepare a series of gold sulfur complexes in the expectation that they may show improved performance. And this really summarizes some of the selective studies to just give you a comparison and show how the differences in performance with catalysts prepared with these various gold complexes. Now, the results I'm showing in this are largely all at using with a gold loading of 0.1%. In comparison, for reference, the catalyst prepared from aqua regia is down below. We have a 1% gold under these conditions as before, where we had about 52% conversion. As we now go into the various cyanides and related ligands, you can see improvements in performance, and the gold 3 cyanide is quite good. But of course, as we expected, the gold 1 cyanide was very much better. And fortunately for us, the use of the idea of using the sulfur ligands turned out to be a good expectation, and you can see the dramatically better activity and with the use of the sulfur ligands. And here you see with this thiocyanate, thiosulfate, and then even better was thiourea. And this really became quite a landmark for us, in that it demonstrated it was the first use, and we could patent this, where it was the first use of sulfur-containing complexes in the preparation and use of gold as a catalyst for this reaction. And it really was significant, because it actually then subsequently has changed quite the way and direction that a lot of the studies have gone into the use of an exploration of gold as a catalyst in searching for mercury-free alternatives for this reaction. If we look at this in a bit more detail, in the use of thiosulfate as a ligand to prepare these complexes, it's actually quite simple. And this gold thiosulfate was well known, and the crystal structure was already published in 1974. So as you expect, you have the gold center, and it's a linear cation with your 2 thiosulfate ligands. And the preparation for us actually now becomes quite simple, because you can really just take gold chloride in water, add your thiosulfate, and you immediately get immediate reduction to form the sodium gold thiosulfate. The corresponding oxidation product is the sodium tetrathionate and some sodium chloride. So the reaction is now quite benign, and again, this was important in our selection of thiosulfate as a ligand over some of the other sulfur ligands, in that it made a preparation that was very amenable to us and environmentally benign, in that although we are trading slightly lower activity, it's a huge benefit for us as a catalyst manufacturer to use a starting or raw material that is non-hazardous and environmentally benign. So now, rather than having, again, as in the aqua regia case, we can now simply do this reaction in water. So we just take the gold chloride, dilute it in water, add the thiosulfate, form this, impregnate it onto the carbon as a straight, simple impregnation from water, dry it to give the active catalyst. So this was important for us as manufacturer of a catalyst, because, as I say, it meant we have a benign preparation, so that takes away a lot of cost and difficulty in the preparation of the catalyst, but it also, of course, avoids a lot of environmental issues. The material that we are using are non-toxic, and of course now for large-scale manufacture, this is now becomes quite amenable and quite simple. And that's really, again, was important, because we realized that if we're going to make significant changes in this industry, given the huge cost and quantity of catalyst that is being used, having a complicated manufacturing process would be quite difficult and would make the catalyst costly, whereas a simple process like this would allow us to make the catalyst and still ensure that it is economically attractive, even though it has the small amount of gold there, which I'll come back to later. So when we now look at this catalyst that we originally prepared. As you see, this is the comparison against the 1% gold on aqua regia. So you see the gold in the surface layer. When we come down and do the corresponding cross-section and elemental mapping on the gold prepared from the thiosulfate complex, you can see we get the same deposition of the gold around as on the surface layer, highly dispersed gold within the first 1 to 200 microns from the surface. And the reason it's much more diffuse is because of course the much lower gold loading in the material. And again, at this point we had done a lot of characterization, and we had really a pretty good understanding of the operational requirements and its potential as an active catalyst, as a replacement catalyst for this reaction. So again, for the XIV's characterization we looked at here was during use, you could see, well, there's actually a very much slower degradation of and conversion either of the gold 1 species either to gold 3, or the degradation, there's very little degradation to gold metal, and you see even after quite extensive use, there's almost no gold particle formation on the catalyst, and you can see the catalyst is dominated with a gold sulfur species. And this really was consistent with our expectation that the gold remains in the stabilized +1 oxidation state. The complex is retained on the carbon support and survives at these typical reaction temperatures, which can even, as you'll see in later slides, will go up to about 200 degrees. But we did notice that on extensive use, and now you're talking long-term use, there is slow reduction and disproportionation to form gold nanoparticles. So it has the similarities and is consistent with the earlier gold catalyst that deactivation is formation of gold nanoparticles, which then effectively remove the gold as active species. This really then gave us the encouragement to start a pilot plant trials. And what you see in here is in the green line is the typical profile and conversion profile, with now plotted it as a productivity rather than a straight time of line, as the deactivation of the mercuric chloride and carbon catalyst. So this would equate to about 6 to 9 months of operation. And again, the reason this line stops is this is a typical conversion at which the Chinese producer will remove the mercuric chloride catalyst and replace it with fresh material. And in comparison, now the 0.1% gold on carbon, you can see even after 3,000, a productivity of 3,000 kilos of VCM per kilo of catalyst, it still has very, very high activity and again, a very stable activity, despite various shutdowns and restarts, etc. So it showed us that the catalyst could be quite robust and actually was quite tolerant of a lot of process upsets. One feature of this and the way these catalysts and reactors are run in China is they're run with very, very slow and low space velocities. So it's very low feed, long residence time through the catalyst bed. However, the reaction zone is actually is a small reaction front that then with time moves down the bed. So and the challenge is as this reaction is so exothermic, is then to limit the heat generation in the reaction zone. So at this point, this really led us to looking at this and scaling up and trying to persuade the VCM producers to look at this in terms of a commercial and full-scale replacement of their mercury chloride catalysts. And this really, I thought, would be interesting just to just go through a little bit, because this is really for many areas where the science and the engineering come together and become complementary to each other. And that really, to persuade a VCM operator of a VCM plant to even test or consider replacement of a catalyst, as a catalyst supplier, we really, it is quite crucial for us to be able to give them the confidence in the use of this catalyst in terms of catalyst handling, operation, and really we need to provide them with a technology package, if you want, an operational manual, because, for them, it's actually a huge challenge and risk to move and replace a reactor that's running well with something alternative that they don't, and they won't put in something they don't know, and that we can't be sure, because for them, they couldn't afford either a catalyst failure or a runaway or uncontrolled events. So really, it's a case of, for the VCM producer, it's a case of risk management, and for us, it's actually giving them enough confidence to run with the catalyst, and that it will do what it should do. So this really changed the focus and the work that we had to then do in JM, which is really, and again, as you see, it's dominated now by more engineering aspects of really, and I've just listed a number of the features that we needed to provide the information to the producer of, for example, how to load the catalyst into the reactor, how to deal with precious metals in contrast to dealing with mercuric chloride. And they want to know how to start it up, what conditions, and at what conditions it will run well and what conditions it won't run well, and what performance it will have. Will the catalyst survive shutdowns, restarts, and of course not give any unexpected performance issues? And then ultimately, will the catalyst run for the sufficient length of time, and that it won't be poisoned by impurities in the feeds or such likes? And of course, ultimately, how do they then shut this down and unload the catalyst and return it for refining, recycling, etc.? And in our case, particularly to get the gold back, to recover the gold for reprocessing into fresh catalyst. So this really set us down quite a different journey as part of our engineering teams, which has really dominated the later years in getting this catalyst commercialized. But having done that, really, the good news is we were really successful here. And at this point, it's nice to be able to say the catalyst has been fully commercialized and its performance has been validated in several Chinese or by several Chinese VCM producers in several reactors. And again, what I'm showing in this plot is the red line is the performance that we had in the earlier pilot plant, and this was of course run at a slightly lower space velocity, so and that's why it's maintaining slightly higher conversion. The blue line is commercial operation in a full-scale full plant, and of course running at now higher space velocity, so the catalyst is operated a bit harder. You can see the various process ups and downs, and again we're showing the data up to for about 12,000 hours online. So it's in practical terms, that's about a 1.5 year operation, and the catalyst is still well above the threshold at which it would be discharged when it's dropped to about 60% conversion. And at this point, we haven't really done any recycling or regeneration within the reactor. So it's clearly, showing very, very good and stable performance. The line actually carries on a lot further, but I've only shown it to this point. When you look at this, and perhaps it's easier to see as a productivity point of view, where again at over 500 days in the reactor, so now I've just shown it up to 10,000 hours operation, you can see the productivity of kilos of VCM per kilo of catalyst. It climbs pretty well, but when you run up obviously at the higher GHSV space velocity in a full plant, you get the greater productivity. And as you can see, the line just continues. There's no, we're a long way off the point of deactivation and requirement to swap the catalyst. From a productivity point of view, it's interesting in that when you're at this sort of productivity of about 3,200 kilos of VCM per kilo of catalyst, you're having a turnover productivity of about 10 million moles of VCM per mole of gold. So much higher productivity than the equivalent of what you can achieve with the mercuric chloride catalyst, where at the end of its lifetime, you're at best getting about a productivity of about 80,000 moles of VCM per mole of mercury. And so the short answer of this is that, and the good news for us is that now several of the leading VCM producers have switched their reactors and reactor trains to operate on the gold catalyst, and it is now is reaching more increasing commercial acceptance, and particularly as the operators are now becoming much more experienced and familiar with the operation of these catalysts, so the performance and productivity is getting better and better as more reactors are operated with this catalyst. As I said to you, it's one of the things we did notice, and it was quite apparent from the early scientific work on this, is the deactivation of the catalyst was due to the formation of gold nanoparticles. And interestingly enough, this really sets off a side reaction in which you grow these carbon nanofilaments, grow during use, and it appears as sort of like a spaghetti on the catalyst surface. And you can see at the tip of the nanofibers are these metallic gold particles, and again with the metallic core. And interestingly enough, these nanofibers are really polyacetylene. They're not formed from product poisoning. But really, this we saw as the next challenge here to, if we can minimize this polymer buildup on the catalyst, that's important from a performance and productivity point of view, because of course generating unwanted carbon filaments isn't good for use of the acetylene, but also it makes unloading and discharge of the catalyst quite difficult because the extrudates now link together. So this really led us into developing a second generation catalyst in which we've now incorporated silicates into the preparation. And what happens is as these catalysts then are deposited onto the carbon, the silicate deposits on the carbon and then is converted into silica. And this surface silica then either simply surrounds the gold particles and avoids sintering and nanoparticle formation, or it basically simply covers the carbon surface and prevents this carbon nanotube formation or retards it, really. And so when you look at some of the SEM imaging and analysis of the catalyst, so this is the gray picture is really a surface electron microscopy of the catalyst surface, and then now doing elemental mapping of the same image. You can see here the gold, as before, the expected high dispersion of gold covering the surface, and again the silica being reasonably well distributed across over the surface. There are some larger, that's a larger blob of silica there, and of course the oxygen linking with the silica as well as it's forming this silica overlayer. If we now look at the performance of these catalysts with the silica doping, now here we are running them at very high temperature. This to obviously to look at it under accelerating aging conditions. So we're running at high temperature and high space velocity. And what we see is the non-doped. So this is the first generation thiosulfate catalyst. Deactivation over time, and the much greater stability of the catalyst with the silica doping in the preparation. And so from this, again, we see quite a significant benefit in the lifetime and improved productivity or conversion. And these materials are now being evaluated at full commercial scale. And again, this was something we could patent a number of years ago. On to something slightly different. Of course, we haven't quite stopped there, and we looked at again several other gold alternatives, and really it was an interest for us to see, was the performance of these catalysts, was it really specific, and and were we dependent on these sulfur-based complexes, or really could we find other ways of improving the performance of these gold catalysts? And this is work we had done really in a long-standing academic collaboration with Cardiff University, and really we knew from our work that the limiting factor, as mentioned before, was the lack of stability of the gold chloride center. But then again, from also other work that had been in the meantime done and published in the literature, we reckon that using nitrogen-contained ligands could be a means to again achieve greater stability of the gold chloride center as an alternative to the sulfur complexes. So we really prepared now a whole lot of gold complexes based on nitrogen ligands, and of these, the use of N-methyl pyrrolidone, as shown, the structure is there. This showed actually very good performance, so we investigated this in much more detail, and really what we ended up with is a new family of gold catalysts based on this complex. So we're now forming an AuCl4 complex stabilized with the NMP ligand, and this we could then synthesize and characterize, and we were able to get the single crystal structure of this, and the material we could crystallize it out as single crystal yellow needles. And here you can see the structure. So you have the AuCl4 center, and then in the usual expected square planar arrangement, with then stabilization and links at about long range interaction to the nitrogen of the NMP ligand up there in blue, and down below here at about 3.7, 3.9 angstroms. And the NMP ligand then hydrogen bonds, and that takes the proton from the AuCl4 and links to a second NMP ligand. So you've formed this now framework of NMP molecules with the gold, and then stabilizing and linking to the coordinating to the gold center. If you look at the arrangements in the unit cell, you can see the gold sitting directly above or below the nitrogen of the NMP, and again the beautiful symmetry as you'd expect in a monoclinic structure. And when we looked at these from a performance perspective, in the VCM reaction, you can see this was really the only alternative that we found that had performance that was really matching on to what we had seen in the thiosulfate complexes. So we have really pretty much comparable activity. And again, this in these catalysts, we see stabilization and the gold being deposited on the surface as a monomer, single atom complex, which then has this high and stable activity under these reaction conditions. And again, in this regime of around about 130, which is where the commercial reactors are operated at. And again, this is something we've been able to, let's say we have a patent application on this, which again will appear fairly soon now. I'll just then move on to something which is really a sort of more future perspective here, and that's really what this has now allowed is, of course, if you look at the sustainability of this whole acetylene hydrochlorination process, in that the main source of power and CO2 footprint that results from this is really, if you take in the carbide part of the process where you're using coal partly as your power source and as well as a carbon source, you end up burning a lot of the power for heat to generate your acetylene. So this gives you a very, very large footprint. But what the current technology and people are now working hard to do is, if you start to use green electricity, so now renewable power sources, and you really use the coal or methane as a carbon source to produce the acetylene, you can have a huge reduction in the CO2 footprint. And this now, coupled with the use of gold instead of mercury, really opens up the landscape for producing VCM by this route. And so, having taken away and eliminated the mercury problem, this opens up now a lot of new alternatives as new technologies to replace the old hydrochlorination process. And so really, in conclusion, what we've shown is gold can be a really viable and technical alternative to mercuric chloride, and is capable of these much higher productivity, and actually operates it as a good drop-in replacement under appropriate relevant conditions that the existing reactors can run under. And so this really starts to put gold well on its way to join the family of all the other precious metals as a viable catalyst for bulk chemicals production. And again, I have a lot of people to thank here in that, of course, this was a significant team within Johnston Matthey. We've been working on this now, as I said, for about 15 years. And this was really split between our research center, doing a lot of the analysis, the engineering team doing the process development and all the engineering aspects, and of course the JM China team doing all the work to get this catalyst into commercial supply, and all their work with getting this commercialized within China. And also significantly was a lot of work to support this. All this project was through the group of Graham Hutchings at Cardiff University, and a series of very, very talented postdocs and students that have done a lot of the sort of fundamental characterization and provide a lot of the underlying science of the catalysts that we've developed. So with that, I'll thank you and open it up for any questions.
Thank you very much, Peter, Dr. Peter. It was a very nice talk. I'm going to open for questions. So let me see if Diane, if you want to.
Thank you very much, Peter. It was wonderful to see all these developments. Maybe, I don't know if you have any question in the chat, Caetano, but I can maybe start with one question.
Yeah, you can start it, yeah.
I have many curiosities about these developments. First of all, I believe it's so important to have a gold catalyst possible to be used in real industrial facility. This is very important for all of us that are working in developing gold for the last maybe 10, 20 years. I was curious about the synthesis process, if you have think about something different. For example, if you start with the complex with gold thiosulfate or thiourea, you do the complex and then you impregnate in the preformed structure catalyst, if I understood well.
Yeah.
Did you see, in this case, we still have mobility of the whole complex on the surface for aggregation, I mean. Did you think about using functionalization of the support and then the complexation of gold on something that is more fixed, more stabilized on the support as a ligand, for example?
Yeah, we of course we explored quite a bit of this, and really we found that actually the deposition of the gold complex is actually so facile that really, and especially at these very, very low loadings, that you're really ending up with a single atom complex which actually bonds and adheres to the carbon surface pretty well, because of course the extrudates that are already very functionalized with all the as it's a steam activated carbon normally used for this. So there's a lot of oxygen functionality on the surface. So the gold, does deposit very, very well, and as very homogeneously over the surface. We were fortunate that we found we didn't need to functionalize the surface much further, but other catalyst producers, and again, there are a lot of studies where people have functionalized the carbon with, again, nitrogen ligands and other things to increase and stabilize the gold deposition in that way. Again, we then felt that, and this is really what led us to look at these nitrogen complexes, but again, we felt making the preformed stabilized complex was advantageous rather than functionalizing the whole surface. But it's of course, there are many approaches, and again, I think it's from a commercial perspective, it enabled us to stay with the existing carbon support rather than having an extra process to functionalize. But I'm sure there will be a lot of openings for improvements, and I would, we would love to see more and more work done on these things, because with time there's such a large requirement of catalysts that actually, and in the details of the reactor technologies, that there will be many requirements, and different catalysts and different formulations will be needed.
And we have two questions on the chat. Maybe I can give it to
go
Dr.
ahead.
Johnston. So two questions come from Giovanni Bruno, and the first one is regarding to how long did it take to develop the golden carbon catalyst and test it on the commercial scale?
We started the project in 2007, and really the catalyst, it took us probably 2 to 3 years to get a good working understanding of what was at that point the gold aqua regia catalysts. And really by about 2011, we had we had found that the gold thiosulfate catalyst had potential. We really then moved fairly quickly through the pilot plant trials. That took another 1 or 2 years. That by about 2013 gave us the confidence to build the catalyst plant in China. We had existing facilities, so we could put it in there, because we recognized that, and it's a bit of a catch-22, that you needed to be able to produce enough catalyst to persuade the industry to test the catalyst. So we had to actually take quite a brave move to build the plant on the expectation that the catalyst would be fine. So we commissioned that and had that operational in about 2015. And really, since then, probably the next 5 years was dominated with all the large-scale trials and performance evaluation at the various full-scale trials at the VCM producers, and really that till we got complete validation of material was probably about 2 or 3 years ago. So really the whole story from beginning to end is almost a 15-year cycle. You could say cut a few years off because it was already known. So maybe about, in reality, about 10 years, which again, for us is quite typical of the time it would take for a catalyst to go from concept to reality.
And the other question, Dr. Johnston, is regarding that he would like to know if the cost of the synthesis of the gold and MPC catalyst is high, and the viability for commercial application.
No, again, that's more current work that we're working on, and there we have now got to the point. This is, of course, now much still in its early stages, but we have fine-tuned and found a number of alternative routes to doing the synthesis that now is quite facile for us, and we've actually simplified that down into a very, very easy route that we can make the material. So from a cost point of view, it's actually not dissimilar from that of the thiosulfate catalyst. And of course, where the difference for us will come is that this catalyst we envisage to be used in different plants, or either in the secondary reactors rather than the primary reactors, where the duty is quite different. So the importance is not so much in the cost. It's actually, you know, different catalysts for different requirements.
Yeah, and another question that you have in the chat is, how do you see the development of a catalyst based on Earth's abundant metals and metal oxides?
You know, this is something we deal with a lot, of course, being a precious metal producer and largest supplier of precious metals for across the whole chemical industries. And what is clear, of course, at the moment and currently, the use of precious metals is dominated in autocatalyst applications. But as we expect that these situations are quite dynamic, and that, as for example, we expect that as the demand in autocatalysts decline with the electrification of vehicles, that the availability of precious metals and the relative availability of them changes enormously. And of course, the other part of that is, as that changes, the use of other metals increases as well. So what's important is not so much the direct cost and use of the metals, but the relative use and abundance of the different metals. So, you know, whereas at the moment, and again, given that, you know, because of the cost and of course availability, the importance with the use of whether it's gold or other precious metals is actually the recovery and recycling, and they are, of course, very, you know, that has to be very, very efficient, otherwise, so the economics wouldn't work. So really, that is fundamental to the use of these metals. But of course, everything balances against the other metals and availability, and I could imagine with time and as further work is done in these things, that whether precious metal, mixed metal, base metal catalysts will also find and grow in application and use. So it's a dynamic situation that we are very, very conscious of.
Yeah, thanks a lot again. Liane, if you have further questions.
I was curious to know if you can tell us, besides this very interesting replacement of mercury for a gold, and that's easy to understand, is well accepted that gold will replace mercury, and this is something good for the environment, and there is many advantages. Is there any other process that gold will find a place in industry?
Yes, there are increasingly so, and again, the good news for us and you is it actually, there are quite a number of oxidation reactions where there are in the fine chemical industry where gold is being used, and quite in those applications is really as gold nanoparticles. Mm-hmm. and quite a number of technologies and reactions are being done using gold in the oxidations. So that area is growing quite a bit. And then also gold is used, of course, quite extensively, as you know, in alloyed and in combination with, for example, palladium, and you have the usual palladium gold alloys are used extensively for whether it's VAM production and and related other of these, call it oxidation type reactions. So really, you know, the use of gold is growing and has grown quite extensively.
Okay, so
but of course, I hope with time this application will dominate, because again, with the size of it, it would be a real change in the use of gold. Although saying that, because gold is actually readily available, and so much has been mined and there are so many gold bars sitting in vaults that actually, even if everything was converted, it would only use about 1% of the world's gold supply.
Interesting.
So
interesting to know that.
Interesting on the availability of of gold around.
Okay, and just maybe a final question. You showed us the catalysts and a nice micrography showing that gold is on the surface of the pellet. This is something that bothers you, or was okay? Did you expect gold to go into the pores of the materials, or this is not a problem? I was curious about that.
No, it's actually an advantage for us. It's actually what we hoped for, because especially the way these reactors are run and the reaction itself, it's all mass transfer limited. So having a thin surface layer maximizes the utilization of the gold. And that's really what was key here, that we didn't want to minimize penetration of the gold into the catalyst. But again, fortunately, it worked in our favor.
Okay, excellent. So I don't know if we have more. We don't have more questions in the chat.
So thank you very much again, Dr. Peter Johnston. It was a really pleasure to have you here in the RCGI Colloquium series.
So thank you very much.
Thank you as well, and thank you again for the invitation. And it was an absolute pleasure and an honor to give the talk to you all.
Thanks a lot.
It was very inspiring for me, and I believe for the students that are listening to your talk. Thank you very much.
No, thanks again as well.
Thank you.